Hello guys, welcome to Simple Solution. This is section 1 in which we would look into molecular dynamics programming. So this is part 2 of the series. In this part we'll look into Lennard's potential and how to evaluate its force. We'll look into a few subtleties which would help us write a more efficient code for evaluating the force and potential energy faster. So, evaluation of the force is the most computational part of a molecular dynamics simulation. So, it is very helpful if we can write a more efficient code in this part that would greatly reduce the uh, time required to run a single simulation. So, Lennard-Jones potential can be of many types. One type is 12-6 potential. So a 12-6 potential basically means that the power of one sigma by r is 12 and the other is 6. So here in this expression for epsilon gives a sense of the bond energy between two particles, and sigma gives a sense of bond length, and r is basically the distance between the two particles. So Lennard-Jones potential here is a pairwise potential, which means that there needs only two particles to find the potential energy. We rewrite the potential energy in such a way as the advantage of writing it in such a way is that we need to evaluate sigma by r power 6 only once, and we can use the same value again. So how we are trying to make the code more efficient is that we need to know this rule of thumb that dividing two floats is very computationally what do you say taxing, but as compared to multiplication, addition, and subtraction. So what we would try to do is reduce our float to float or double to double division as much as possible. So we'll look into this more in the code. So basically we rewrite this so that we have to multiply less, we have to divide less, and so on. So to find the force, we just take the partial derivative of potential energy with respect to the position of one particle on which we are evaluating the force. So we do a partial derivative. We get a expression such as this, and then when we use the expression of r and do partial derivative of r with respect to xi, we end up with a simple expression such as this. Here, if you notice, sigma by r power 6 is also present. So not only do we need the value of sigma by r power 6 in for calculating potential energy, but we also need it for calculating the force. So we don't have to do extra computations to find the potential energy and the force. So we'll write a single code in which we can evaluate both of them together, and that would reduce our computational time tremendously. So let's continue from where we left off in the previous video. Since then, I have added a few comments on the code which explains what the function does. So the first function here, min_dist, basically returns us the difference between the x, y, or z coordinates of two particles, whichever is passed to the function. And the second function which we defined returns the square of the distance between two particles. We require square of the distance because both the potential energy and the force, as you can see, has even powers of r. So we need only the square of the distance and not the distance itself. And to put more light into this, we should know that finding square root of any float or double is very computationally taxing, and while multiplying two floats is not. And so we would also avoid the taking root of function of floats and doubles as much as possible. So let us define a function which calculates the Lj force and potential. So calculates LJ force and potential. So let's return double force LJ. So here this to find the force between two particles, I would need the position of two particles, which would be x1 and x2, like the previous function. X2 dimension. These both are vectors of xyz coordinates of two particles. We'd also need to update the potential energy, for which we'll pass the potential pointer to the potential energy. And so to find the force first, we need to evaluate sigma by r per 6 for both potential and force. So we would do that by finding sigma by r per 2 and multiplying it 3 times to get per 6. So we can get r squared by the distance function, which we defined earlier. So we need to pass just x1 and x2 to that, and we'll get the distance. So dr2 is double, and now we need to find the sigma value. So let's say the sigma value is stored in S2. Then let's define sigma by R2 as sigma by R2 is equal to sigma 2 by uh, dr2. So sigma 2, we can now define sigma 2, S2. S2 is equal to sigma multiplied by sigma. So now we have sigma bar 2. So we now will define sigma by r bar 6, sigma by r bar 6. So sigma by r bar 6 is equal to sigma by r power 2 multiplied 2 times. 2 into sigma by r 2. We change the potential energy by adding, so let's write it, potential plus equals to, we add to the potential value the value of sigma by r per 6 into sigma by r per 6 minus 1. So also there are two other additional terms which you need to multiply, 4 into epsilon, but to if you multiply 4 into epsilon, to each of the potential energy term will be multiplied it for many times. But if we add up for all the pairwise potential and then multiply 4 and sigma, we only multiply it 2 times. So this way we would multiply those in some other function which we'll come across later, and that would decrease our float to float or double to double multiplication by the order of n. And now we can define the value of force. So let's call it val, and to val we uh, store some constant ESP, which would be our 24 epsilon. So instead of 24 epsilon, we will store ESP as 24 epsilon by mass, because we do this because we would be only needing the value of acceleration and not the force. So we would store the value of 24 epsilon by mass in ESP as a global variable, and then for to this we would have to multiply sigma by r per 6 into 2 times of sigma by r per 6 minus 1, and divided by r, sorry, divided by r square. So this would be the force or the acceleration in this case which I would be requiring. So we'll just return this value. So I haven't defined the values of sigma and ESP, so let's go ahead and define them. So hash define, hash define sigma equals to 0.3, hash define epsilon equals to 1.5. Okay, so made a mistake here, it's not equal to, it's just space. Okay, so and then we define something called double s2 equals to sigma into sigma, and double ESP equals to 24 into epsilon by mass, and hash define mass for now as 1. We can later change it to the mass of particle which we'd be using, and we can also actually remove this part. So basically I don't want to calculate sigma square every time, just once, because it's a constant. So in a simple problem, we'll have just one particle, so we're dividing it by mass and storing it in ESP. So there are two ways we can go when we have multiple particles. One way is that we define the mass ratio and just define by one base mass, and then multiply ESP with the mass ratio to get other acceleration values. But for us, we just have one particle system, so we'll just divide by mass in the global variable. So that's it, and now let's go ahead and define the main function. So now I have to do some test cases to check my minimum distance, and force LJ functions are correct. So let's define an int main for that. So now basically we will be running the code and checking it, and we'll add a return 0. The test cases which we'll be doing are as follows. So sigma, if we take sigma as 0.3 nanometers, when the distance between two particles would be equal to sigma, my potential would be equal to 0. When r is greater than 2 power 1 by 6 sigma, where is at the force will be attractive, so r is equal to 0.4 nanometers is greater than 2 power 1 by 6 sigma, and we'll be testing with this value. And when sigma is less than 2 power 1 by 6 sigma, force is repulsive, so we'll have r is equal to 0.2 nanometers. And to check my PVC is working properly, I'll take x1 as 0.1, 0.1, and x2 as 0.9, 0.8, and 0.7. So the distance between using the PBC nearest image would be, if we took the length as 10, so the distance between the nearest image would be basically 0.2 here, 0.3 for this, and 0.4 for this. So the distance should be something like 0.5385. So we'll write a code to measure these and check if our code is correct. So we define first the x positions. So double x to two particles, 3 dimensions, equals to, first one is 0.1, 0.1, 0.1, and then we have 9.9, 9.8, and 9.7. We have to pass a potential, so we'll define a double potential. We'll initialize potential as potential equals to 0. Okay, let's go down a bit. So the potential is 0. Before we check the force LJ function, let's check the min dist and distance function. So we'll printf. We would print out the difference in x, minimum distance in x, minimum distance in y, minimum distance in z, and the distance, and then enter. So min dist x0 0 and x1 0. So we'll just copy this. Oops. We'll just copy this and then paste it two more times and change the indices to 2, which is for z, and 1, which is for y. And then finally we'll have a sqrt distance function, and then just pass x0 and x1. So, and then yeah, okay, so this should do it. So let's see. So I hit the run button. Okay, compiled, and then so as you see, 0.2, 0.3, 0.4 and 0.5385. So our distance function is correct. Now let's just check the force function. For force function, we would do a simple case, so we would just keep it one dimensional. So if the difference between 0.1 and 0.5 is 0.4, and we'll keep the rest same in x, y and z coordinate. So we can find the distance, but we don't need to. So here we would now printf do first printf the force. Oops. Okay. Yeah. What printf the force? So we'll do force lj, which would take x of 0 as x coordinate, x1, and x of 1 which as x, the variable x2, and this x0 is variable x1. So we need to pass the pointer of potential as well. So I'll give the address of potential, so that should pass the pointer value. And after I've done that, so once the force function is calculated, the potential value of potential will be updated because we are updating it here. So now after the printf has been run, so basically we have the value of potential in the variable called potential in our main function. So we'll just print that. To find the force, what we're getting from here is not just the force, we are getting a magnitude called val. So to this I have to multiply x0 of 0 minus x1 of 0. So this basically gives me the force on x direction on particle index 0, that is particle x1. So yeah, now we should run it. Now this would give a perfect value. So here the force value is positive because we are calculating force on index 0 particle, which is in point 1, which will be attracted towards point 5. So the force in x direction should be in the positive direction towards the second particle, which is at point 5, which is shown here as the force is positive. So now let's check what happens when r is 0.2. So we'll just change the value of 0.5 as 0.3, so that should basically change it to 0.2, and then let's see what happens. So now the value is 0.2 and the force is huge and negative. So it's now repulsive in nature. So this test cases make sure that our force, distance and minimum distance function is correct. So again, if you like this video, hit the like button. Comment down below if you have some better idea for better algorithms to calculate force or the minimum distance or distance. Also, if you think that if I have done a mistake, I'd like to check it out. I'm always open to suggestions, and subscribe if you want to get more of these videos.